Yes, some student network issue is there.
Yeah.
That is a bit delay, but I think it's now okay. I hope my screen is visible.
It's visible, sir.
Okay, okay. So we'll start because of the time is I think 8:10.
No, they're
That
connected,
is
sir.
6:10.
Everybody is there now.
Yes. So now we can start. So welcome in for week 4 fluid mechanics live TS session. So the content is of week 4 lecture 1 was about the application of conservation of momentum, the Bernoulli equation, and lecture 3 was about the application of Bernoulli equation. So in regard the first equation is this. In the Bernoulli equations, the uh, first question is visible.
Yes, sir, visible.
Okay, okay. If visible, then you can try. Then after we'll discuss some concept. Now the first question is about uh, the Bernoulli equations used for pipe flow, and each term represent what? If
Sorry, it is one A. Sorry, one A.
okay, you are telling the option number A.
Yes, sir.
Okay, and someone also please everyone write your answer in the chat box. Open your message dialog and write your answer in the chat box. Week 5 content is live now, right? I think. Pradeep,
Yes, sir.
week 5 content is going on right now.
Yes, it is going on, sir.
I think some solution is also available on the portal. You can check.
Yes,
Week,
sir.
week 1, 2, 3.
Yeah, I'll just see, sir.
Yes, yes. Solution of week 1, week 2, and week 3 are available. You can check also.
Thank you, sir.
So please everyone give your answer about the first question. The Bernoulli equation used for a pipe flow. Each term represent option A is the energy per unit weight, option B energy per unit mass, option C energy per unit volume, and option D energy per unit length. Okay, someone telling the option number B is correct. Okay, let's check which option is correct. For the Bernoulli equation, you know all, it is a very common equation in the fluid dynamics. That is the pressure head plus velocity head, that is the datum head is equal to constant. In the Bernoulli equation, each term represent what? This is the option. This is the question. You know all about the what is rho z?
Uh,
That is a unit. If you go through the unit kg per meter cube
okay.
into,
That is the weight, sir. Specific weight. Sorry.
yes, this is the weight, not, you know, the gamma is the unit of gamma is Newton per meter cube. So here the question is the Bernoulli equation used for the pipe flow. Each term represent the, this is the nothing but this is represent your the density and G. You all know the specific weight, definition of a specific weight. So this is represent the energy per unit weight, not energy per unit mass, right?
Yes, sir.
And the option question 2 is uh, water flow is steadily down in a vertical pipe of a constant cross section, neglecting the friction
Sir.
according to the Bernoulli equation. Neglecting the friction according to the Bernoulli equation, which option is correct? Or basically option 1, A, B, C, D. The option A is about the pressure is constant along the length of the pipe, velocity decrease with height, pressure decrease with height, and the pressure increase with height. Water flow is steadily down in the vertical pipe. Let's consider a vertical pipe is here. This is the vertical pipe, you can assume, and water is flowing like that. So here option you just,
Flowing down. It is flowing up or flowing down? Flowing down.
yes,
So what is it flowing up or down, sir? Flowing down.
yes,
Flowing down.
flowing down means here is the inlet, this is the inlet, and the downward is the outlet, right?
Okay, okay.
So this is the downflow from top to down, this is the up, down. So this is the, and option is, this question is very basic. If you go through the basic concept, how the water flow, how the pressure responsible for the water flow, then you can easily get this answer. Okay, for option B, for option 2, someone telling the option C is correct. Okay, Pradeep is telling the option D is correct. Okay. This is the flowing water, not the steady water, not the still water. The water condition is in dynamic condition, not in the static condition. So here the static condition is not valid. Pradeep, you just guess the, I think D option.
Yeah,
Okay,
that,
I
that's
will.
correct.
Oh, I will discuss. I will discuss. Just I am waiting the 1 minute more. The other participants, please write your answer in the chat box. Whatever you are getting in your mind, please write your answer in the chat box. Then I will discuss some concept why, which option is correct and why this is correct. Okay, Vidya is telling the option D. Okay, and another one, another participants, please write your answer. Okay, now I am going to discuss. In case of static, just who is telling the pressure increasing? Okay, in case of static, you know all, if the water in a static condition, let's say this is the wall and water is static condition, not flowing. So what will happen as you go down, the pressure will increase in the static condition when there is no movement in the fluid. But here is in this case the movement of fluid. As you all know, the movement occur when the higher pressure to lower pressure. You all know from the very basic beginning, from the very basic concepts. You all know the water flowing only when the pressure higher pressure to lower pressure. So water is flowing up to down. You just think the here water will here the pressure will be more as compared to that location. That's why water flowing from this direction. So as you what is here as you the question is this water flowing steadily down in a vertical direction vertical pipe of a constant cross section. So as you vertical pipe means you are starting from here, that is the initial condition you are here, and you are going this direction, that is the you are gaining the height, that is the in terms of this height is negative if you represent the your axis like that. This is the z axis, x axis and y axis. So this is the z, but you are starting, let's you assume your pipe is at that location. This is your pipe and you are starting from 0 0 0 coordinate, x is 0, y is 0 and z is 0. You are starting from here, your height is increasing, but negative increasing, you just forget about the negative sign, you just think the your height is increasing from inlet to outlet. So where only possible water flow only possible only when your the inlet pressure will be higher as compared to the outlet pressure. So as increasing your height, the pressure decrease with height. So here pressure is something, let's say assume just for 1000. At that location your pressure will be 900. At that location your pressure will be 800. So this type your pressure will be decreased. That's why the flow is possible from one location to another location. In river similarly, if your pressure is high in the upstream and pressure low in the downstream, then only flow possible. So this is the basic behind this question. So option number C is correct for that. Okay, now we move on the next question.
So,
Please, yes, someone.
so I have a doubt with the Bernoulli's equation. So actually, the Bernoulli's equation is conservation of momentum or energy. I mean, we will be deriving that Euler's equation from the momentum equation, isn't it? And by integrating the Euler's equation, we will be getting this Bernoulli's equation. So, but the Bernoulli's equation is actually the conservation of energy. So,
Yes,
actually, the Bernoulli's equation is conservation of
energy,
momentum or energy.
conservation of energy, not momentum.
So, but we are deriving it from Euler's equation, isn't it? Integrating the Euler's equation,
Yes,
and so
yes, yes,
Euler's equation is actually derived from the conservation of momentum equation.
yes. Oh, because okay, okay. Now I'm getting your doubt. Okay, just wait a minute. Here, what is here the all term in the equations, that is the your this z, that is your datum head, and this is your velocity head. our kinematic head, and this is your pressure head. Basically, these all terms represent the energy in terms of this is the your pressure head. What I am discussing here, pressure in the upstream and downstream, this is the one type of energy. Kinematic head, that is the your velocity, how much kinematic head, half mv square. And z1, this is the potential head, rho gh. So these are the energy, these term is the energy. That's why here is the all energy is constant, we are telling.
Yes, sir.
Okay. Oh,
So
oh, by the time you will be clear, your doubt will be clear. We have lots of example we have on the Bernoulli equations. So by the time you solve the question, you definitely your answer, your doubt will be clear, and I will discuss more about it. You don't worry.
okay,
Yes,
sir.
please.
So will we be discussing about this in the later? I mean, when a questioner asked about what is the origin of that equation, is it? I mean, when we derive it, when we derive one equation from another equation,
Yes,
uh,
yes.
uh, you understand what I am meaning?
Yes, yes. You are telling we are deriving the Bernoulli equation using the Euler, right?
Yes, sir.
After the Euler, okay, we'll discuss about more. Don't worry.
Okay, sir.
Yes, definitely I will discuss. Yes, please go on the question number 3 and write your answer in the chat box. The question number 3 is the equation gz v square by 2 and del p by rho is constant along the streamline, hold true for. That is the your this equation is given in the question number 3 is valid only along the streamline. You know the whole concept, how for deriving the Bernoulli equation we derive the equation along a streamline, not only one streamline. Let's say you just solve, then I will discuss some concept behind it. This is the very interesting concept I will discuss. So just you give your answer in the chat box for question number 3. For question number 3, Vidya and Pradeep is telling option number C is correct. Okay, option C is correct. How C is correct? I will discuss. Don't worry, Francis is also telling. Okay,
What is the difference between uniform flow and steady flow, sir?
yes.
What is the difference between uniform flow and steady flow?
Okay, okay, definitely. I will discuss. Before going on the answer, I will discuss, then I will declare the final answer of this question. Okay, I think please everyone give your answer. If you joined here, then you can give your answer. Okay, now we'll discuss. Okay, Pradeep, you are asking the steady flow, right? And uniform flow. Steady flow is nothing, just your flow parameters like velocity, change in velocity, or pressure, and other flow parameters, right? With respect to time,
Yeah.
constant. That is the no change, right?
Yes, sir.
For example, consider a pipe. or you can consider a channel, open channel, whatever. Let's say you can consider open channel. You're looking from side view at the particular location in both cases. You just at 8 a.m. you measure the velocity here 2 meter per second, right? After 8:30 your velocity, if your velocity is 2 meter per second, then this flow is known as the steady flow. I think you are getting by this example. And uniform flow, what is uniform flow? For uniform flow, you at the 8 p.m., for this I will write here, at 8 a.m., this timing is just I taken the randomly, at 8 a.m. your velocity at throughout your channel, throughout your pipe should be same. That is V is equal to, let's say, 3 meter per second, right? At each point, should be same. But in case of a study, only a cross section. If you are checking here at 8 a.m., the velocity should be different from that location. At that location your velocity was 2 meter per second. Same time at that location your velocity may be 2.5 meter per second. At 8:30 am velocity is 2.5 meter per second, but here is the same. So at a cross section your velocity is same at a different time. This is known as the steady flow. But in case of uniform flow at both cross section, at that cross section, at 8 a.m., if you are checking the velocity in both cross section should be equal. That is a 3 mm. Not only 2, everywhere your velocity should be same. This is known as the uniform flow, and mathematically we can write your velocity with respect to a space is constant. Right, this is the steady flow and a definition of a steady and uniform flow. Now coming on the question.
No, no, sir. One question. Like in case of steady flow, the measurement will be from only one particular spot, and while in case of uniform, it will be throughout the channel.
Yes, no. In case of steady flow, no need to only you check at one cross section. You check also another question, another section, right? You
Yes.
can check at another section, but your velocity may be different at another section also.
Yeah, got it.
In case of a study, but
Yes.
at same section your velocity should be same with a different time. If you
Yes.
are checking at that section your velocity should be same at the different time, right?
Yes.
But in case of uniform, your velocity will be same at each section,
Yes. Yes.
right? In
Yes.
case of a study, no need at that location, at same time your velocity should be same. This is your not definition of a study. A study definition is at a particular section with different time your velocity should be same. Velocity or other flow parameter like pressure and
I
everything.
got it. Yeah.
Yes. So I think you are getting.
Yeah.
Now
I got
coming
it.
on the
So,
question number 3. Yes.
in the case of a tank which we derive that Orsilis equation, sir, if there is a tank and there is a hole at the bottom of the tank, then
Yes.
the flow from the tank will be unsteady, isn't it?
Yes.
So, in such condition, can we apply this Bernoulli's equation?
Yes, yes. Okay, okay. I will discuss this concept just after the. Let me explain the question number 3. Then after I will discuss. Okay.
Okay, sir.
So now moving on the question number 3. uh, In question number 3, the equation this is given. You all know Gz plus V square by 2. And before discussing this question, now I want to discuss one more concept of the incompressible and the compressible flow. Compressible flow means your density not constant, right? And the incompressible flow, your density is constant. Okay. So here what is given, and integration dp by rho. In this case, you are looking here, your density is not constant because it is the your density is not constant because it is the inside of your integration. Whatever you have seen, p by rho z plus v square by 2g z is equal to constant. In this equation, your density is constant, but in this equation, your density is not constant. So this equation is valid for steady, frictionless, compressible flow, not incompressible. This equation, P by rho z V square by 2g Z equal to constant, this equation is valid for steady, frictionless, incompressible flow. Now hope this question number 3 is clear to all of you.
So the correct answer is option C.
For which? Option number 3.
Yes, sir. So,
Question number 3. You are telling the no, question number for 3. Option number A is correct. What I am telling, if your equation was that at the place of that P by rho z V square by 2z plus Z equal to constant, then your equation was valid for option number 3. But here equation is what given, the integration of dp by rho, that is here rho is your not constant. So that's why in case of not constant rho, this is the case of compressible flow. So option number A is correct for this question.
so but that dp by rho, the rho is actually constant, isn't it? Integral, it's actually dp is the derivative and rho is in constant.
Oh, you are telling we can consider here the rho is constant. Hello, Francis. Hello.
Derivative, isn't it?
You are telling the we can assume here the rho is constant, right?
Yes, I am asking that.
Oh no no no. Here that's why the integration sign is given here for that only. For just you address, just you know the here the density is varying with varying. So that's why this is the only the your integration sign is indicating for that. Your integrating sign is indicating for that your the rho is the function of something. So it is changing. So that's why it is changing means the flow is
Okay, so
the
since the rho is given inside the integration, it's actually a function of dp. It's actually changing.
yeah this is that's why this equation is given like that. That is the gz v square by 2 and your dp by rho.
I think, sir, the question is where is integration of dp by rho? I think the y not t. I think that is the question.
So no, your equation is given like that. I think some typing mistake here. Your
Yeah, that is.
equation, yeah, your equation is like that. Whatever I am writing here. Okay, and Francis was asking about some tank concept. Okay, I will discuss. Okay, for that I want to take a new slide.
So, so I have one more doubt that actually the Bernoulli's equation can be represented in this two form, and for the first form, it can be applicable for the compressible flow also, and
Yes, yes.
the
Compressible flow
second
means what? Compressible flow means
constant
what?
form
Fluid.
only applicable for the incompressible.
Yes, yes. What I am telling, you just let me write here also this equation.
So actually, that jet flow to jet and everything will be compressible, isn't it?
So actually, I'm not getting your voice is breaking here. You just tell again.
So my doubt is actually is the Bernoulli's equation can be represented in these two forms, and in one form with the integral, we can use it for the compressible flow also, and
Yes, yes. For compressible flow,
the one with that constant form.
yes. If your rho is constant, then it is valid for the incompressible steady flow. And if your rho is not constant, then compressible flow. Because of the definition you all you know, that's why here the option number A is correct for that question.
So actually, the second case is actually a subset of the first one.
Yeah, we can derive only for that. Uh, just wait. Here, if we
So if
consider,
someone asks about the
yes, yes.
write a Bernoulli's equation, we should be writing the first one with the integral
No, no. If someone asking you write the Bernoulli
general form.
equation, yes, you write the Bernoulli equation. First, you need to tell I am going to write this Bernoulli equation by this assumption. Your assumption, if your assumption is like that, before you writing the Bernoulli equation, if you are writing somewhere, you just write the assumption. The equation for this assumption is the steady, frictionless, and incompressible. If you writing like that, then you can write this equation P by rho z and V square by 2g plus z. If you are writing the assumption is that steady, frictionless, and the compressible, then you can write only this. You write the integral one. Okay, before writing the Bernoulli equation, or if someone asking to you, then you can also ask for compressible flow or incompressible flow, or otherwise if you're not asking to that person, you just tell the assumption first and you can write your equations. Okay, generally people are writing this when
Okay,
some,
so
yes, when someone asking the Bernoulli equation, generally people telling this equation P by rho z and V square by 2z plus z is equal to constant. But this is not the correct way. Correct way is that you just before the telling the equation, you tell the assumption, then after you describe your answer. This one. Then after write your equation. So now coming on your question. Okay. So this is the tank. Francis, your question was that.
yes, in the tank it will be actually steady flow and steady flow. So can we apply the Bernoulli's theorem here?
No, no, we
Since
cannot
the
apply.
Bernoulli's
We
theorem
cannot
is
apply. We cannot apply because of for that type of question. If someone telling you you apply the Bernoulli equation, the already assumption is given. The flow should be steady, and you can apply only the Bernoulli equation for just your for just sake of understanding. Let's say your water is flowing like that, right?
so, but for an open tank, it will be actually unsteady, isn't it? Since there is no flow generation inside
Yes,
the
yes.
tank,
In the
it
practical
should
way,
be.
yes, yes. In practical way, this is the unsteady flow. But for your solving the question, people are assuming. This is the unsteady flow. Okay, this is the steady flow for your just solving the questions. But in the practical way, when you go for in the practical, there is not the case of steady flow. For just sake of understanding, people are frame the question like that. Already assumption is given. The flow is a flow as a steady, not an steady.
So in the actual case, will we be using any other formula or anything, or we will
Yes,
be
yes,
using the same one?
definitely. If you are going to design something, then you can not you can only you cannot design using the Bernoulli equation. There is a lots of procedure for designing such type of tank. So for solving
So
that type
in
of,
that case, which equation will we be using for that case? I mean the name of an equation. Is there any we'll be using for general case?
for designing purpose,
Yes, sir.
for unsteady you are telling.
Yes, sir. For unsteady flow.
Yeah, definitely several equations are there. You can go through the Navier-Stokes equation. But Navier-Stokes equation again having some problem because the non-linearity. Then you can go through some numericals method for solving the non-linearity of the Navier-Stokes equation. So I think Navier-Stokes equation, I don't know in your syllabus was having or not. I think I have. In
No, we
the
have that
yes,
question.
yes, yes. So when you go through, na, then you can definitely your doubt will be clear. So for the meantime, you just assume for your solving the problem, the flow is steady, not unsteady.
So the diagram that you have shown here, the
Yes,
tank diagram, the
yes.
flow is one-dimensional. How can it one-dimensional when you're changing direction? Sir told it is one-dimensional in the class, well, in the lecture. There is a similar figure was there. Yeah, he said it is one-dimensional flow. Uh, so how to know it is a one-dimensional flow? I understand that, but in this case, it should be two-dimensional, is it not? Like it is
Yeah, this
contained.
is two dimension because length is there and width is there.
Yeah, that's right. Yeah.
Or some other some if the here if like that, if you draw the actual tank, this is a three dimension.
Yeah, three-dimensional. But
Yes.
there was just, I think there is one of the lectures, Sir's lecture. In such a case, it is shown one-dimensional flow.
Okay.
Uh,
Maybe some other aspects are was telling.
right. Okay, sir.
Okay, so now here point is that the only the lots of streamline is flowing out from that locations. So only your Bernoulli equation is apply only one streamline here. You just apply at that location your Bernoulli equation at that location. At both location the pressure is atmospheric. So you write your equation P by rho z, and already assumption is given here. The steady and incompressible. P by rho g v square by 2z plus z, that is the and equal to P by rho z, that is a 1 z1 P2, this is the P2. At P2 your both are atmospheric, and v square by v2 square by 2g plus z2. If you are taking the datum at that location, your z2 is 0, but z1 is some height is given in maybe h. You just consider atmospheric pressure here and atmospheric pressure here, both side cancel. Velocity at v1 it is 0, so z1 is equal to what? V square by 2g, v2 square by 2g. This is only if you want
So
to.
actually, at the opening of the mouth, the how can we assume that the pressure is atmospheric? The pressure will be different for that point, isn't it?
No, 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 no. Pressure is atmospheric because of, okay, okay. Pressure is atmospheric because it's open in the atmosphere. This is not connected with the another pipe.
But
You
the
know,
flow at that point will be having a pressure, isn't it? If we take a nose and at the opening of the hose, the it will be having a different pressure, isn't it? Even though it is open to the atmosphere, I mean, the flow will be having some pressure, isn't it? Other than the atmospheric pressure. So how can we assume that
No, no, no.
that
Okay, okay, okay. Just let me explain. If your tank is like that, your Bernoulli equation is valid. Streamline, your streamline is like that. At that location, inside the pipe, pressure is different. But at the outlet of the pipe, here the atmospheric pressure is applicable on your whatever water is flowing. So pressure is equal to the atmospheric pressure, right? But inside the just inside the uh, just before the mouth of the pipe, your pressure will be different as compared to the atmospheric. So for applicable Bernoulli equation, why we are applying here? Because at that location we don't know the pressure, but at that location we know the pressure. At that location we know the pressure. That's why we are applying the Bernoulli equation at the mouth and at the top of the tank, because at both places the pressure is atmospheric. If you sum, you just from the very basics, if someone is open in the atmosphere, that the atmospheric pressure is applied at that location, you know already. So with this concept you can calculate the what is the velocity at the mouth. That is
so if we take such assumption, then actually we are calculating velocity with that atmospheric pressure, isn't it?
yeah, yes, please tell again.
Actually, the velocity of that fluid is due to some pressure hit, isn't it? But when we take that point outside the uh, tube and
Yes, yes,
factor,
yes. The
so
pressure
the
is, yeah, pressure is at that location outside the just your pressure is atmospheric pressure.
so velocity corresponding to that atmospheric drive will be calculated, isn't it?
Yeah, based
Instead,
on that only we are calculating. No, that's you whatever I have. I write the equation here. The velocity we are calculating with respect to the atmospheric pressure. With respect to the atmospheric pressure, because P2 is also equal to the atmospheric and P1 is also atmospheric. So whatever your V2 is your whatever V2 here is coming. Actually, it is practical. If you open something in the atmosphere, that is pressure, atmospheric pressure. At that streamline, the pressure is atmospheric just outside the at that point also and that point also. With this concept you solve that type of problem.
okay, sir.
Okay, Taylor, if you have, Francis, if you have some doubt, then I will show in the next class some classical examples on that, right? So your doubt
Okay,
will
sir.
be definitely someone writing something. Okay. Okay, now moving on the question number 4. The Bernoulli equation is an equation of, just write your answer in the chat box. This is a very basic. For okay, for question number 4, option C is correct. Yes, yes. Now we'll move on the next. Pitot tube concept. Pitot tube is used to measure what? Static pressure of the flowing fluid, dynamic pressure of the flowing fluid, total pressure of the flowing fluid, and the surface tension of the flowing fluid. And question 6 is the if the velocity distribution is rectangular here means the uniform. Okay, for 5 question number A. Okay, after this both question will take some 5-minute break. Okay, someone telling the option number C is correct. Pitot tube is also used for measuring the velocity. Okay, let me discuss the question number 5. Let's assume a pipe flow and you are putting here the pitot tube. Height is like that. Water is flowing in that direction. As water flow in that direction, your height will be increases. Let's say at that point your water height is increasing in this pipe. Let's say H. So this H is gained by what? Due to the velocity, due to the pressure, and also due to the and whatever. If you taking the datum at that location, then H will be different. If you taking the datum at that location, your H will be different. So you can tell the datum also, and you can neglect also as per this depend on your datum. So what here the pitot tube is measure the total pressure of the flowing fluid. Why? Because this pressure is increasing in the tube due to the velocity, pressure, and also datum. So option number C is correct for question number 5. For question number 6, if the velocity distribution is rectangular, the kinetic energy correction factor is what? That is the this case. You all know the velocity distribution generally like that. But in the question is given what? Rectangular type, that is the like that uniform. uniform flow. So what is? In that case, for question number 6, it is equal to the 1, equal to unity for question number 6. Option D is correct. What is happening? Some network issue is there. Some network issue is there in my side. Okay. Now I'm sharing again my PPT. Okay, why PPT is not showing?
So actually it is not visible. It's a black screen.
Yes, yes. I don't know why PPT is not. Just wait. Now PPT is visible.
No, sir. The screen is visible.
PPT is visible.
Actually, it's not the PPT. I am seeing the your screen, me screen.
Okay, okay. I don't know why. Okay, let me join again, right? Just wait a minute. PPT, why not swing? Now visible. PPT is visible now.
Yes, sir, now it's visible.
Okay. Now just wait and tell me again. Now it is not visible. Hello? Now my screen is visible only or PPT is visible? Hello? My screen is visible or PPT?
Yes, sir, your screen is visible.
Okay. That's why, but I want something. Why? Okay, now it's coming. Now it is visible, right?
Yes, sir.
Okay, please go through the question number 7. The hydraulic gradient line represents the sum of what?
So actually, that PTO tube question was incomplete, isn't it?
Yes.
PTO tube question.
Okay, okay, okay. Oh, that's in that question we just miss out, right? This one?
Yes, sir.
Okay. In question number 5, what is given? The pitot tube is used to measure what? Basically here static pressure or dynamic pressure, a total pressure or the surface tension of the fluid. As you insert the pitot tube in the pipe flow, what you have seen, your height will be increased in the pipe, and this height will be increasing as your velocity, pressure, and your datum head. It depend. This height is depend on that pressure, velocity, and all. So using the pitot tube, you can calculate the total pressure of the fluid flow, not static, because pitot tube you are using in case of the water flowing. So a static pressure, this is not a case. So it's your correct answer is the total pressure of the flowing fluid. The option number
So,
yes,
is the PTO tube and PTO static tube same?
yes.
So, both of them are same. PTO tube and PTO static tube.
Pitot tube and pitot static tube.
Yes, sir. By
Ye-
just meaning PTO tube, whether it is actually PTO static tube or is that another instrument?
Yes, yes. Whatever you are telling, okay, no problem. Oh, but in this case, what you are telling the your static pressure of the flowing fluid, right?
So my doubt is actually whether the PTO tube and PTO static tube same or both of them are different instrument.
Okay, for that I need also check because I don't aware about the pitot static tube.
So
So
one more thing is if actually at the point the flow is stagnant, isn't it? The
yes,
flow is
yes, at that.
so it should be measuring the static pressure or
No, 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 no. You don't confuse with this concept. Uh, Here is the pressure is measuring the total pressure of the fluid because of the your press. This height is depend on your velocity, pressure, and as well as your datum. By the you can datum neglect here also if you taking the datum at that location. So it is a different datum for datum is different issue, but your height is depend on velocity and pressure what is in the inside the pipe. On that only this height you can get. So with this height you just measure the what is the pressure inside the pipe. So this is the pressure due to uh, this is the total pressure, not only by the your only velocity or not only the pressure. This height is gaining with the combination of both. So that is why.
So the flow becomes stagnant. Doesn't matter that it is the flow is actually becomes stagnant over the so the whole energy of that flowing fluid is converted into that fluid inside the pipe. Is it like that?
Oh, you are telling the energy of pitot tube?
Yes, actually, the flow is actually becomes stagnant at the entry point, isn't it?
Yes,
So,
definitely stagnant. If not stagnant, then water, yeah, definitely stagnant here at that location. As
so
what I am telling, as you increase by somehow, if you going to increase some pressure inside the pipe or velocity you are going to increase in the pipe, then this height will be affected by both. If you are going to any disturbance at that location, let's say at that location you are going to disturb by the increasing velocity, then this height will be different. If you are going to disturb with pressure, then height will be different. If you are going to disturb with by the both, then your height will be different at that location. So that is why a pitot tube measure the total pressure at that of a fluid flow. Okay.
okay, so it will be both sum of the static and dynamic.
Yes, 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 definitely. By
So
that, yes.
one more thing is that we are able to measure that height of the column since the whole energy of that fluid is will be converted to that column inside the pipe. I mean, the fluid inside that pipe will be converted to that pressure head.
Actually, I am not getting what you are telling.
What I am asking is, if a questionnaire asks about the energy conversion in that point, why we are able to measure that pressure at that point, what will be the answer? I mean, why we are able to measure the height pressure at that point using this?
You are telling why height is measured at that location.
No, sir. If a question is like that, what is the principle behind that measuring the pressure at that point? I mean, the total kinetic energy is converted into that pressure head.
Yes,
Is it?
yes, yes, definitely. Yes, yes. The kinetic energy is converted in the this is the in terms of height and your pressure also.
We are actually calculating, finding out velocity or the pressure at that point. Pitot
Yeah,
tube.
pitot tube actually we are using for measuring the velocity, but question is here frame in the different way. Okay, so
Okay, sir.
basically for that purpose we apply the Bernoulli also. If you go through the lecture, then I think sir is explaining the very well. Okay, for your question, the pitot static tube and pitot tube, let me, I will tell you in the next class. Basically, I don't remember about that. Okay, for that, for this question number 6, if the velocity distribution is rectangular, the kinetic energy correction factor is what? For that, basically, the in general case, the velocity distribution is like that, but in question is given the rectangular, that means the uniform distribution throughout the depth. So what is the your kinetic energy correction factor? So this is a equal to 1. For that you can go through the derivation in the, I think sir was, I don't know completing or not completing, but you can go through some books. You definitely you can get the derivation about that, why it is equal to 1. So for just,
So, for applying the Bernoulli's equation, the flow should be invisible, isn't it?
yeah, inviscid should be, flow should be
So,
inviscid.
can we are not able to apply this flow through the pipe, Bernoulli's equation inside flow through the pipe, since there will be a velocity distribution and viscosity of the.
No, no, you are telling flow is inviscid. No, no, you can apply. Why? If no, no, you just in the real life problem there is every fluid having some viscosity, right? But
Yes, sir.
for mathematical formulations, for mathematical formulation, we considering, like for in case of water, we considering for apply the Bernoulli equation in the pipe, the flow is inviscid. For mathematical formulation, you just imagine, you just apply water is flowing in the pipe, and you are going to deal with how the water is flowing in this pipe. So you want to formulate in the mathematics, you want to formulate this, the, the movement of the particle in the form of mathematics. So for that you need some assumptions, and if some assumptions, so that's why if you are going to solve with the viscid, that is the in case of Bernoulli equation your flow is inviscid. If you are going to solve, if flow is having some viscosity, then you need to solve the Navier-Stokes equation. In the Navier-Stokes equation, the all consideration is uh, the all consideration, that is the viscous flow is considered in the Navier-Stokes equation. So for Bernoulli equation only, for mathematical formulation and for calculation and for understanding of your numerical problem, so we consider the flow in the inside the pipe. In actual condition, there is no viscous free flow, right? So when you are going to design something, you need to solve some Navier-Stokes equation and other equations also. So here you can just think, for your solving the problem and basic understanding, the Bernoulli equations is given.
So for the Bernoulli equation, what are the total assumptions? I mean, it should be inviscid, frictionless, and the
Yeah, yeah. Frictionless means why? Inviscid. Frictionless meaning is inviscid.
okay, sir.
Yeah. So for Bernoulli equation, in conclusion, Bernoulli equation is applicable where the fluid should be inviscid, right? Okay, as you go with the
Sir.
different lectures, with the I think like week 6 or 7, then definitely you got the sum about the Navier-Stokes equation. Then definitely you will have confidence in that. Okay, now moving on the question number 7 and 8. Please solve the questions. The hydraulic gradient represents the sum of what? The pressure and kinetic and datum head, pressure head, kinetic head and datum head, pressure head and the datum head. Please write your answer in the chat box. Yes, everyone participates. Okay, now I'm opening the chat box. Okay, please everyone write your answer in the chat box for question number 7 and 8. And everyone, if you have interest in the fluid mechanics, so then along with NPTEL lecture, you follow some book, like whatever sir is discussing the classes, the Sinjal Simbala book. You can go through. This is a very classical book, and lots of figure is there in the book. So you got the lots of confidence. To,
So do you have the PDF of that book?
no, I think on Google is not available.
Actually, the PDF drives, some of the sites are not actually working. That's why.
Okay, because here we are, I am following the not PDF. I am following this hard book. In my college, the hard book is
Okay,
with.
sir.
Oh yeah, I don't know. Let me check. These people solve the
So
question
can you once
number
again say the name of that book?
single symbala fluid mechanics. Just I'm question is visible or my screen is visible to all of you.
Yes, the question is visible.
Okay, okay. Now I'm going to write something for okay.
Yeah, the book reference there in every lecture of a sir.
Yes,
In
yes, yes. I
also
think on the,
also the course it is there, course module is there.
yeah, I think this is not, you cannot download.
No, sir, not available online. I bought
Yes,
it
yes.
1200 rupees, very expensive.
Yeah. These are the foreign books, so that is a definitely.
No,
But
well,
they,
Indian edition, but print is not as good. It's a bit lighter actually, bit light. Not uh,
okay,
it is a photocopy probably.
okay, okay. But I think some book is there. If you saw, if you search, I think some student was telling one times the book is available online also. I don't know. Just I am writing here the symbol symbala fluid mechanics. So for question number 7, Pradeep, you are telling the option number C is correct, right? Other people also give your answer in the chat box. The hydraulic gradient line represents the sum of, and question number 8. Okay, okay, okay. Don't worry, I will tell. Okay, we'll move on the solution part. So hydraulic gradient, by definition, it is defined as a hydraulic gradient is the sum of, for hydraulic gradient I am going to write the short form Hg, is the sum of what, the pressure head plus datum head. This is the definition of the hydraulic gradient line. If you are considering here a pipe and you just considering your datum line is this, the mid of the flow, one piezometer here and one piezometer here. Definitely water is flowing from this side to this side, the pressure at that location will be more. Let's say this is the H, H1, H2. So this line is known as a hydraulic gradient line.
So it's actually connecting the each head height of if we connect consecutive piezometers nearby.
Yes,
Sir, actually, is the hydraulic gradient is actually if we connect consecutive piezometers nearby, and we will be connecting the h value.
yes, 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 yes. That is I am telling.
Okay, sir.
But height should be due to the only pressure and datum. But in case of total energy line, your height also Here consider the V square by 2G and V square by 2G. So this line represents the total energy line. So conclusion is that for hydraulic gradient line, only two pressure head and the datum is considered. For total energy line, or the pressure head, datum head, and the velocity head is considered. So this is the very basic difference between both, and this is a very basic questions in the fluid mechanics. Most often the people are asking about this hydraulic gradient and the hydraulic energy line. So please you remember always. Now moving on the next.
So for the total energy line, kinetic energy will be additionally added to it.
Yes, yes. For the total energy line, the kinetic energy, that is the your kinetic head is added in the, and you can also say this, the total energy is equal to hydraulic gradient plus kinetic head, right? So you can represent like
So
that also.
this viscous energy loss will be represented in which line? I mean,
Yes,
if there is there will be friction losses in it.
friction
So
losses.
yes,
Yeah,
those
if
friction.
yes, no. If your friction losses is there, then definitely at that point, if the pressure is P1, and at that point pressure was, let's say assume at that point the pressure was P2, but this P2 was when the pipe was very smooth, right? When the pipe is, that is you are going to take the friction loss, then in the second case when you are going to take the friction loss, you, let's say at that point the pressure is P3, P2 is greater than P3, because due to the some friction loss your pressure will be decreases. Okay, so line will be different, line will be bit below as compared to smooth and frictionless, right?
So for the if there is friction, then the it will be below the hydraulic gradient line.
Yeah, because the loss of pressure due to the friction.
Okay, sir. So hydraulic gradient line is actually excluding that presence of the friction. Uh,
Yeah, it's depend on question, frame of question. What type of question is framing? If already given the pipe is smooth, and if pipe is smooth, then you can draw. If you in your question is given the pipe is friction, then for that location also pipe is friction. For that location also pipe is friction. If someone telling you compare the line, you compare, let's say one pipe is there and one pipe is there, everything is same, only the this line is some friction and this line is very smooth. So in that case when you are going to compare, and then you can draw like that of, if for that
so,
some height is there, for that some height is there, right? For that some, if someone telling you draw the line only in one pipe, for that some line is there, for that some line is there, only different line is there, but someone is telling you draw this line here also. So what you will do, you just draw this line like that below, because of the pressure, because of the friction. This line represent the your second case, and this line represent the this already the piezometer is inserted in this pipe for that case.
so
Okay.
for as a conclusion, the hydraulic gradient line is not excluding the friction. If there is friction, then there will be difference in the pressure, and we will be having another hydraulic gradient line. Is it like
Yeah,
that?
definitely. Your same pipe, you just think for same pipe, these two cases is not there. For different pipe, your these two cases there. Let's say you have the another steel pipe, stainless steel, and you have some copper pipe. The friction of the stainless pipe, let's say F1 and F2 more, right? So for that hydraulic gradient and everything, cross section and pressure, whatever you are getting, and velocities, or everything is same for both, but hydraulic gradient line will be different due to the friction only, right?
Yes, sir. The difference will be due to the friction.
Yes, yes.
Okay, sir.
So now we are moving on. This is done. Yeah, this is done. Yeah, this is a very basic. Whatever we are discussing, this is the similar question 9 and 10. Please solve the question. I think question number 10 is from your first introduction class. Ankur, you are asking about what? I am not getting. Are you from IT? Yes, I am from IT Guwahati. And the teacher in YouTube was different. Yes, definitely different, because I am the TA in this course in the fluid mechanics. And whatever the Professor Subhasis Datta is definitely different. I think some interaction meet was there by the Professor Subhasis Datta on the, I don't know which date, but one day was interaction. You everyone come on that day. I think you got some notification about that also. So you come on that day and you can clear your whatever you have the basics problem, basic confusions. You can clear on that day also. Okay, for question number 9, which option is correct? A, B, C, D, and for question number 10. Okay. Yes, please just match the answer. V square by 2G, what is? Whether piezometric head, velocity head, datum head, or pressure head. Okay. Nadeem is telling the option number B. Okay, let's see. Please everyone give your answer in the chat box. Yes, please everyone give your answer in the chat box, whatever you are getting. Okay, someone telling option number D is correct. V square by 2Z is represent what is P by rho Z. Before I think from last 3 to 4 slides I am discussing only that Bernoulli equation, and this is given only the Bernoulli equation. Only just breakdown in the option number A, option 1, 2, list 1, 2, 3. In the list 1, option 1, 2, 3, and list 2, option 1, 2, 3, 4. Please match. I think some mistake in the typing. 1, 2, 3 at the place of 1, 2, 3 in the list 1, A, B, C is there. I think some typing mistake. A, B, C is there. So for, okay, now I am moving on the, for option number 10, for question number 10. Okay, option C is correct. Okay, let me explain.
So this piezometric head means a pressure head and a datum head.
Yes,
Okay, sir.
for the velocity, this is the V square by 2Z, it is represent your velocity head. So this is you just A, B, C. Here I think some typing mistake. For A, option number 2 is correct. P by rho G, this is your the pressure head. For B, your force, and Z is a datum head. So for C, this is your 3 is correct. 423. 243. 243. Option number B is correct for that. For question
So
number
can we
9.
say that since the piezometric head is actually sum of diatom and pressure, it can be the hydraulic gradient?
Same thing, same thing. Same
Okay,
thing,
sir.
same thing. The pressure head, the piezometric head is the you can also, if you are civil engineering, you are from civil engineering background, this piezometric head concept is used in the soil mechanics also. So you always remember the piezometric head is the combination of pressure head as well as datum head. Okay, now moving on the question number 10. The kinematic viscosity
So
is equal to, yes.
one more doubt is actually if there is a friction in the fluid, it will be mainly affecting the pressure. It won't be affecting the velocity head. The
What
friction.
you are telling?
Sir, if there is friction in the friction inside
In
the
the
pipe,
pipe, okay.
it will be mainly affecting the pressure head, or it will be affecting the won't be affecting the velocity head.
No, no, it will affect velocity also because it will be affect velocity. Why not? You know the was sleep condition, no sleep condition. I think in the first lecture, no sleep condition, right?
Yes, at
So
wall it will be no slip.
yes, no sleep. If your
So
surface is, yes, yes,
yes, sir, continue, sir.
yeah, it will be affect if your surface is like that, and in some case if surface is like that, definitely this is your surface is like that, let's say small.
So why I ask that doubt is actually while we are drawing that hydraulic gradient light, it's actually the pressure showing the pressure head and the datum head, isn't it?
Yes, 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 yes,
Even though there is friction in it, but for the total line it will be there will be the kinetic energy change will be representing that total energy, isn't it?
yes, yes, yes. You are telling in the energy gradient line, in the energy gradient line we are drawing only the whatever is given, we are drawing only the pressure head and the datum head, right?
Yes, sir.
But if the pipe is friction, pipe having the friction, this line will be decreases, right?
Yes, it will be lower than that.
Okay, okay. And if the pipe having the more friction, then what will be happen with the velocity head, right?
Yes, sir.
Okay, for that doubt I need also some clarification. Okay, so with for that doubt I will clear in the next class, right, Francis? So you just remind me, right, in the next class
Okay, sir.
on Monday, same time 6 to 8. So you just remind me. I will talk to some my professor and also some book. I will go through some classical books. Then I will definitely come with the solution with this problem, right?
Okay, sir.
Okay. For just now, moving on the next question. Okay, you solve this question. Question number 11 is visible to all of you. Water flowing through a pipe. Hello.
Yes, sir, visible.
Okay, please solve the question number. Water flow through a pipe of 5 centimeter diameter under a pressure of 29.43 Newton per centimeter square, and this is given the gauge pressure, and with mean velocity 2 meter per second. Find the piezometric head of the water at the cross section which is 5 meter above the datum line. This is the very basics. Whatever we are telling from the last previous 4 5 slides. So what is the datum head, pressure head, piezometric head? Or you can definitely write the answer for these questions. Oh Ankur, you don't talk like that. This is not make sense. This is not a good habit. Please, Ankur, don't write like that in the coming session and even in this session also. This is very bad habit. So question number 11, please solve everyone. 5 meter, okay. Water flowing through a pipe of 5 centimeter diameter under a pressure of 29.43 Newton per centimeter square. This is the pressure is given at that location and with mean velocity 2 meter per second. Find the piezometric head. You know all the piezometric head. What is this? Is the combination of what? Datum head and pressure head of the water at the cross section. To find the piezometric head of the water at a cross section which is 5 meter above the datum line. That is, the datum head is here given the 5 and the pressure is what is 29.43. So here the you need to give the answer in the meter. Okay, someone, yes please, within 2 minutes you just write your answer, then I will discuss about the question. Okay, someone telling the 5.2. Let's see. For question number 12, you are telling, okay. Yes, please. Now I want to solve the questions. Water is flowing through a pipe of 5 centimeter diameter under a pressure this with a mean velocity this, and find a piezometric head of the water at a cross section pipe which is the above the 5 meter. Like this is the your datum line and water is flowing like that. So, and also let's say at that point water is flowing through a 5 centimeter diameter. The diameter of the pipe is how much? 5 centimeter. And the pressure, what is the pressure? 29.43 Newton per centimeter square. You need to convert in the meter. 29.43 into Newton is there. For centimeter square you need to 10 to the power minus 4 meter square. So how much? 294300 Newton per meter square. This is the pressure. With the mean velocity is 2. Velocity is given at that location how much? 2 meter per second. Find the piezometric head of the water at a cross section which is 5 meter above the datum line. Let's say assume at that point from this datum line, this is the 5 meter. At that point asking the piezometric head. Piezometric head is what? Piezometric head is a pressure head plus datum head. At that pressure head is something and the datum head is 5. So how much the pressure? This is the pressure. But here asking the pressure head. Pressure head, because you need to answer in the meter. So what you will do for the pressure head, you need to convert in meter. So P by rho z, and water is given already. Water is flowing. So P how much? 294300 divided by 1000 into 9.81. So how much you will get? Let me calculate using the calculator. Yes, please, everyone calculate. 294300 divided by 1000 into 9.81. 30. 30. So you need to put here 30 plus 5. How much? 35. So 35 is the correct answer for the question number 11.
Sir, please explain again, sir.
Yeah, definitely. Sure. Asking the piezometric head, right? Question number 11, I am solving.
Yes, yes, sir, yes.
Piezometric head is the combination of pressure head plus datum head, right?
Yes, sir,
In
yes.
the question, datum head is given, right?
Yes.
And in the question, pressure is given, not pressure head is given. So pressure head, what is pressure head? P by rho z, right? So how much P is given? Pressure is given 29.43, but in Newton per centimeter square, right?
Yeah.
You need to convert in the meter. You need to multiply by 10 to the power 4, right?
Yeah.
So when you calculate this, will come 30 and 5 is the 35 is the answer, right? For question number 12, find the above total energy is asking. Total energy. So for total energy, what you will do? For total energy, you will do what? You just add in the piezometric head plus velocity head, v square by 2g. This is the total energy. How much v is given? 2, that is 35, that is the piezometric head, plus 2 square divided by 2 into 9.81. How much? 35 plus 4 by 2 into 9.81. Calculate. Let me calculate. 4 by, that is the 2 by 9.81. 0.2. So your answer is 35 plus 0.2. 35.2 is the correct answer. Getting?
Yes, sir. Yeah.
Okay. Now we can move on the next question. We have time, lots of. This is a very basic questions. Question number 13. A pipe through which water is flowing having the diameter 20 centimeter at 1 and 10 centimeter at 2. The velocity of water at cross section 1 is given 4. Find the velocity head at section 1. Velocity head is asking. You all know the velocity head is formula what? V square by 2g. At what section is asking? At section 1. At section 1 is asking means v1 square by 2z. Or what is v1? You need to calculate the v1. Already v1 is given in the question 4. So you just calculate that. You put it in the formula and calculate the answer. And write your answer in the chat box, please. Write your answer in the chat box. Anyone please solve the question. Okay, Nadeem is telling the 13.04. Yes, please everyone solve the question. Question number 13. Yes, you can do. Yes, definitely. You use the continuity equation. But here the for question number 13, already velocity is given. you need to calculate the v square by 2z, or that is the, let me explain on the board, that is the 4 square by 2 into 9.81, how much, this is your velocity, that is a 16 by 2 into 9.81. Zero 0.81. For question number 14, what you will do? For the above problem, find the velocity head at point at section 2. So that is a v2 square by 2z. For v2, what you will do? You know the discharge will be same at q1 is equal to q2. That is the a1 v1 is equal to a2 v2. So for calculating the v2, a1 v1 by a2, that is your v2. For a1, pi by 4 into d square, that is the, for a1 0.2 square, why 0.2, because 20 centimeter is given, I am converting here the meter, and velocity is 4 divided by pi by 4 into 10 centimeter for the section 2, that is a 0.1 square, pi by 4 is cancelled. Now how much, here is the 2 to the 4, 0.04 into 4 divided by 0.01, you can neglect here, that is a 16. So v2 is equal to 16, so how much, 16 square divided by 2 in 2z, that is the 16 square divided by 2 into 9.81, that is 13.04 meter. Velocity is 13.04 for question number 14. Okay, now please find the question number, okay, find the solution for the question number 15. Find the discharge in liter per second, not in meter. This is a very basic, only unit conversion. Yes, please. For the question number 15, in assignment, the question is challenging. What type of challenge? Please share here something. Yes, Nadim, you can write here what type of challenge in the assignment. These whatever I am talking, I am dealing here, whatever the question, these are the question from the previous fluid mechanics NPTEL courses. These question is from the NPTEL 2020 I think 20 and 21. So these are the question already in the NPTEL courses run, or same courses in the fluid mechanics, not in the another fluid mechanics, same fluid mechanics. Yes, Nadeem. Why? Because of the in the previous assignment, like NPTEL 19, 20, 21, these type of question was there. So that's why I am dealing with this question. Okay, take some difficult problem. Definitely, in the coming classes, I will take the assignment level, whatever assignment is going on, that level I will take the questions. Okay, sure, definitely. From the next classes, I will take some question like that. Okay, for question number 15, what we will do? Discharge is asking. You all know the discharge, what is discharge, formula of discharge, area into velocity. How much velocity? 4. Area how much? Pi by 4 into d square. 4 is given at that location. D is take, you need to take the d1 square. 4 4 cancel. Pi into 0.04. But you need answer in the liter. You need to multiply here 1000. So how much liter? 0.04 into pi into 1000. 125.66 liter per second. Yes, everyone got the answer?
Yes, sir.
Yeah, definitely. I have some also questions. If someone want to take the screenshot, you can take a similar question. This question was the, I think, NPTEL 2020. Now I am going to show the questions from.
Sir, the question 15 was for head for the section 2, sir. For the section 2.
Yes.
I think it was for section 2, not for section 1. The
So
question
it will
14.
be 1.25 liter per second.
Yeah, maybe some calculation mistake. Let me check again.
I think it should be 0.1 square. Yeah.
For what?
No,
As is constant throughout the pipe.
no. For 15 number question,
Yes.
this question was for number 14.
No,
For
no.
number 14,
Discharge at just discharge at both location will be same. You don't forget the concept of
yeah, I got it. Yeah,
conservation of mass.
yeah, I got it.
If you are going to maybe some calculation mistake, let me check again.
No, I think it's got it.
Area is what? Pi by 4 into d square. That is d is given 0.2, right?
Yeah.
Now area into velocity. Velocity is how much? 4. And you want to calculate in the liter, you need to multiply by 1000. Okay, pi by 4 into 0.2 square.
Sir, it will be 0.02 square.
Why 20 centimeter is given?
Sorry, sir. No, it's not
20
in mm.
centimeter means what? You need to divide by the 100, you will get the 0.2. 0.2. I think you will calculate, I think 125 is a correct answer. Let me check again. 4 into 100,000. Yeah, 125.6 is the correct answer. 125.67 liter per second. Okay, if someone want to take the screenshot, please take the screenshot of the another questions. Very basic question. Visible. The another question 1 and 2. Yes, anyone please tell the option. The new question is visible. Question 1 and
Yeah,
2.
visible, sir.
Okay, you if someone want to take the screenshot, please take. If done, please anyone tell the done. Then I will move on the another question.
Yeah, done.
Okay, now I am moving another. Okay, after that I am moving on another. Same the piezometric head, whatever we are dealing in the previous, the same like that. But this, but what is going right now in the assignment, the current fluid mechanics courses, definitely I have seen the question, definitely some difficulty level is more as compared to this. So it will for you only. And now moving on the another. Okay, please solve. These are the questions, very basic questions.
Sir, in the case of that nozzle, can you show once again?
Which one?
No, there is a nozzle question, isn't it?
Which one? 9.
No, next slide.
Okay, okay, okay. This is the first slide. Now second slide. Nozzle
Yes,
directs
fifth question.
liquid jet. The hydraulic gradient line of the jet. Now moving on the next. The piezometric head of the flow.
Yes, sir, actually, that can you explain that nozzle question? What will be the difference?
What questions?
No, that there is a nozzle question, isn't it?
Nozzle.
Fifth question, yes.
Yeah, this is just simply telling if your nozzle is directed like that from the horizontal 45-degree, right, and water is flowing from that like that, right, after some
Yes, sir.
distance it will be fall on the ground. So it is asking the hydraulic gradient line of the jet. What will be the hydraulic gradient? If asking the hydraulic gradient, you know what is pressure, how much pressure, everywhere the atmospheric pressure, right, because it's open
Yes,
in
sir.
the atmosphere. And the datum head, these are the datum head, right, these are the datum
Yes.
head. If just consider at the datum like that, so for fluid particle the datum is this, so pressure is same everywhere. So your is hydraulic gradient line, what is represent? datum head and pressure head. So your hydraulic gradient line will coincide with the center line of the this water jet.
Okay, sir.
Yeah. Now moving on the next slide. Piezometric head. This is the similar question. Kinetic energy correction factor and this you can go through some lecture and you book. You go through some derivation. Definitely you will get some clarification on that. Now moving on this question. Some question is also there. Question 11. Question 12. Only figure is given. Here nothing, only the pressure and velocity is calculation is there. If you go through question, you definitely get the answer. Some note is there. If someone want to take the picture, you can take. What is wake reason? You know the concept of wake, why I have put it here. If some, let's, water is flowing like that in that direction and touch to the cylinder, what will, in the behind the cylinder, the a low velocity zone is created. So this is known as the wake zone, or you just assume the aeroplane is flowing like that. The behind the aeroplane, one region is created where the mixing of air and rotating of air is happening in this region. So this is known as the wake region. And what the effect of wake region is that it reduces the velocity of the your aeroplane or anything is moving in the air and water due to the wake region. So scientists and what fluid mechanics researcher what trying to reduce this wake region, or the inside the wake region the pressure drag is developed. So we are trying to design something like that. The wake region should be decreased and pressure drag will be decreased, so the efficiency of the aeroplane or everything whatever is moving in the fluid will be increases. So that is the concept. When you go through the line by line of this, then you definitely get some confidence. Okay, we'll move we'll meet on the next day. Next
So,
come.
can
Yes.
you address that continuity Bernoulli's equation derivation? I mean,
Oh,
uh,
yes, yes.
actually, it is derived from the Euler equation and Bernoulli's equation. I mean, conservation of mass for the given for the Bernoulli's equation, isn't it? But it's actually derived from the uh, Euler's equation, which is a momentum conservation.
Yes. Okay, Francis, you have lots of interest. Okay, I'm very happy. So in the next class, I will come through the derivation, right? The complete derivation of your this Navier-Stokes, or like, yeah, or your Bernoulli equation and the Euler equation. Okay, then all
Okay,
your doubt will be clear, right? Today's time is completed. So in
okay,
the
sir.
coming classes, definitely I will come with. You have lots of doubt. Oh, that's good. Doubt should be there. Okay, Navier-Stokes also I will discuss from the before. From the Navier-Stokes equation we derive the Bernoulli equation. Not from Bernoulli equation we derive the Navier-Stokes equation. So in the coming classes you definitely get what I am telling, why Navier-Stokes equation, from Navier-Stokes equation how we will derive the Bernoulli equation. You just for undergraduate, uh, the Navier-Stokes equation not dealing the much as compared to the graduate level. So definitely I will come in the next classes with the derivation of Bernoulli equation, Euler and Navier-Stokes equation, whatever.
Okay, sir.
Question number 13, someone asking. Okay. Yes, please note down. Take a screenshot. If you are using the mobile and whatever laptop, you can take the screenshot. Yeah, it's done. It's done. Please write yes if it is done. Okay. Okay, thank you, all of you. We'll meet in the next class on Monday.
Okay, sir. Thank you, sir.
Okay, okay, welcome. Okay, okay, Pradeep. Thank you. Thank you all. Bye bye.